and then we can begin. Today, the first thing I'm going to do is I'm going back. Oh no, first thing I'm going to do is I'm going forward, because a number of you sent me some questions. Some of these questions were interesting and relevant to the topic we just finished with, which is, I think it was the database, if I'm not mistaken. Yeah, the data dictionary and the normalization processes. And this was the first question I had up. If you have a file with fields A, B, and C, and a field A is the key, then you need to add field D. Could you not create another file with field A as the key and field D is now added to the second file? Generally speaking, once you have your database in place and things are stable and finalized, this is the way you will expand your database. You generally won't just add one field. You usually have a couple of fields that are required for an additional functionality that you want to build into the database, and so it won't be one field, it might be a number of fields. However, you would then choose to add them to an additional file rather than change an existing file, because it has the least impact on the database. When we get to talking about views of the physical data, you will see that actually from an application perspective, it's very easy to bury the additions into a file without causing any impact to the existing systems. That we will talk about when we start talking about the logical database. But what we have here is a rather interesting question. Second bullet point, this method would be an alternative to having extra fields in the original file. Yes, and in a large number of cases, it's the better option, simply because it requires far less impact on your applications and various other things. The last point is rather interesting. Then would both these files be at least second normal form? Now, if I look at this literally and we agree that field A is the key, and that means field B, C, and D are all relative to the key, the whole key, and nothing but the key, they won't be in second normal form. They will actually be in third normal form, because there's only a single field as a key. So as long as you follow the normalization methods, then joining two files together with the same key will normalize the new file at exactly the same level as the original file. And it becomes that easy to do that. So it's the question here is, I find once you have a stable database, and I have to keep repeating this because I do not want to be accused of misleading you into believing that this job is easy. The hard part is to normalize your database and get it into a relational third normal form. Once that is done, you're going to have a party because it's easy to add. It's even easy to add extra fields to an existing file. There are many techniques and ways of doing that once you have the database sorted. It's also much easier when the database is sorted to know where certain things have got to go. It's easy to identify where you need to put new fields. So that was the first question. And in fact, the files would both be at the same level and probably set a third normal form. Okay, let's have another one. Watson and AI, I love this one. It's totally, I mentioned Watson and AI, because once you have a nicely normalized relational database, then you can start actually fantasizing about artificial intelligence and Watson type of reasoning systems. And the question here is, you're right, the computer's not thinking, because a computer can't think. But it is also not just a series of questions written by a programmer. That is what we would term a knowledge base, is where you have a whole lot of questions and answers, and they're related together. And when you ask a question, it finds the question and pops up an answer. But on a little bit of research that I did, a reasoning system is what we're talking about here, both with Watson and the AI, is a reasoning system. It's a software system that generates conclusions from an available knowledge base using logical techniques such as deduction and induction. Reasoning systems play an important role in the implementation of artificial intelligence and knowledge-based systems. So that is where it begins. It's a reasoning system. It's not canned answers, because a system can take together and begin to use deduction and induction methodologies. And if you really want to, go to the internet. There is so much written about this, both theory and practice. You have no idea. It's not easy stuff, and it's not easy to read either. But it then devises or deduces or induces a solution. And then it adds that to its knowledge base in the form of knowledge that it can then use in the future. So in fact, it's not thinking, but AI systems are learning. Because every time you interact with an AI system, you're giving it information which it's then using for the next round of deduction. There are two types of systems. One is an interactive AI, where you sit in front of a terminal and it asks you questions and you answer them. And as you answer them, it'll ask you another question, and so it will begin its process of deducing and finally come up with an answer that you're looking for. The other one is a batch system, where you fill in a form or fill in a whole lot of details, and it goes away and does its real deduction and induction analysis over this and comes up with an answer to the question. This is a new animal altogether. IBM has proved Watson is amazing. I've seen some reports on it. And Watson at the moment, as far as I'm aware, is being focused on medical issues. But I can see the technology growing and growing and growing. And in fact, you can do something similar in your own organization. Maybe not as sophisticated, but you can create something that gives you the ability to answer questions or deduce things from your data. But it all, and this is where I stress again, it all comes back to having that data properly, its elements and its construction formally and properly structured in a normalized DB2 relational database with consistent data element definitions. Without that, you're wasting your time. Okay, so that one was sort of not on topic, but it was also fun. When you convert a DDS to a DDL, what is the best way to tell that you have a DDL? One of IBM's best achievements, shall we say, as well as what I believe one of their biggest mistakes. I don't know how it's possible that you can have a big achievement and a big mistake in exactly the same way. But the actual variation or difference between DDS and DDL on the IBM I is almost invisible. It occurs under the covers, and you can do the same things and deal with DDS and DDL files in virtually exactly the same way. And the DDL file is defined in exactly the same way as a DDS physical file. And the only way you can tell if you don't have AO, because AO keeps track of what is DDS and DDL. The only other way is through the DSPFD command, which shows you there's an extra field in that. I can show it to you. Drag this in here quickly. DSPFD space AMWDD. That line there tells you that you have a SQL table. If it is a DDS, that line will not be there. It doesn't say that you have a DDS table. It just doesn't tell you that it's a SQL file type. And that is the only way that you can tell the difference between a DDS and a DDL. Logical files are a little easier. If you do it with a logical file, you can still use you still have to use the DSPFD, but if you use sorry, here we go. Let me get my fingers. You've got the SQL file type there, but on a logical file, you also have the statement that was used to create the SQL table, the SQL index in this case. So you have got the code in the file definition as to how the file was built. So those are the only ways you can tell the difference really between DDS and DDL on the IBMI. Right, let's see, what's the other question? But if you convert a DDS to DDL without any field changes, can the SQL long names be added to the DDL afterwards without it changing level ID? The answer to that is yes. You can also change text descriptions. You can also change column headings. And it doesn't only apply to the DDL. You can actually, with AO particularly easily, but you can, using the alias keyword, you can add long names to DDS files as well. So you can, in fact, take your database, which is a DDS database, and by adding long names to the DDS files, it can look like a SQL database, DDL database, even though it's still DDS. And there are some cases where this is a nice thing to do, to give your client, SQL client users access to your database with long names without having to go through the process of converting those files to DDL. So all of that type of stuff does not change the level ID. And I've got another zinger for you, which is what you've got to be careful about when you start doing this. Keys on a physical file, be it DDS or DDL, do not change the level ID. So I can change keys on a physical file, either DDS or DDL, and the level ID will not change. This is actually quite a tricky one, because if you are processing a file based on a certain key structure, and you then go and change that key structure, you can cause your processing to go completely haywire, because you will then suddenly be processing the records in the wrong order, and you won't get a level check warning because it doesn't alter the level ID. So make a note of that one, because that's particularly important if you are adding keys or changing keys in order to normalize database files. Okay. Here's a future question, which I will be answering in the next, if not today, then it'll be next week. What is the advantage of constraints over triggers or vice versa? There is no advantage of one over the other. They work together, and they each have their own benefits and their cans and can't-dos. Although you can make a trigger do something that constraints do, and you can make constraints do some of the things that triggers can do. But here again, you use the tool for the purpose for which it was intended. And so it goes on. So we'll cover this in a lot more detail when we get through. Brings me to the next topic. This, by the way, is Kruger National Park's one of our biggest tuskers. As you can see, this is a huge elephant, and it's got enormous tusks. It's called Duke. He died in 2001, but he was one of the biggest, heaviest tusks in the Kruger Park, one of the big five. I just thought you'd like to know that. Right. Let's get on to the DB2 Relational Database Components. Now, where we're going with this now is we're starting to look in more, we've talked in general terms about the philosophies of normalization and etc. Now we're going to dig a little deeper into what a relational database actually consists of. I'm not going to worry at this stage too much about the actual definitions. We are going to look at the components that make up IBMI's DB2 relational database. Vitally important to realize that these tools and the components that we are going to talk about have been around since the early days of the 400. Sorry, I'm just reading a comment from Marinus. He was busy working on artificial intelligence today. The components and the whole construction of a DB2 relational database have been around since early AS400 days. That means they have been there inside the operating system, available for use for close on, I don't know, 20, 25 years. And it's my mission in life to make sure that one starts getting the benefits. Everybody starts getting the benefits of something that's been there for so long. It's crazy that we're not using it. So, these are tools to make your life easier. These are components that are going to make the database more intelligent and easier to use and easier to define and more agile and all of these lovely words. And of course, this cartoon again, don't fall into this trap of being so busy shoving your cart with square wheels across the ground and ignore the advantage you can get from doing this modernization job. I'm the guy on the left. Don't be the guys on the right, please. Thank you. DB2 components. The main component of DB2, the IBMI DB2 database, is the physical database itself. That is a set of one or more data files defined to contain physical data. Obviously, it's best to have them normalized to third normal form, these physical database files, because they're going to give us the best balance between flexibility and ease of use. And actually people forget that the physical database file is, in fact, a component of the database and must be seen as such. It's not part of the application. Doesn't belong to the application at all. Okay, I have a date, 1991. So that was when these functions from the DB2 relational database have been available to us. So the physical files themselves, normalized, are the #1 component of a DB2 database. Then, the trick here, it's an IBM DB2 relational database. I stress the word relational, because this is what this database is. It is a set of physical files that are related together by definitions called constraints. These are part of the database. The constraints have absolutely nothing to do with the application. They have to do with the data contained in the physical database and how it relates to other data contained in other normalized tables within the database. There are 4 types of constraints. There are primary key constraints. A primary key, by definition, is unique. And every single physical file in the database must have a primary key, which is unique. Without that uniqueness, we cannot define relationships between physical files. Sorry, tables, for those who want to be purist. We need these unique keys in order to create relationships between files. File A is related to file B. You can't have records in file B if you don't have record in file A. But file A must have a unique key, because if you've got two records in file A, you can't create a relationship because you have a mess. So primary keys on every single physical database file. Then we have additional keys, which are additional unique keys. This is something that people are not aware of. I can build relationships between physical files using multiple unique keys. I don't only have to build relationships on one key. I can have 6 unique keys on a physical file. And I can use those unique keys for relationships to other files relating data in different ways. The other use for a unique key is to ensure that uniqueness is applied to fields that you would not otherwise include in a primary key. For example, a company name. You can make a company name a unique key, which means that you cannot have 2 customers with the same name, even if they happen to be 2 different customers. This is possible, I've seen it. You can't have ABC Shoes as 2 different customers, because you make their customer name unique. You can use unique keys in that way as well. So the unique keys are a very powerful element in forming and constructing a relational database. Then we have a constraint called a check constraint. This is essentially a where clause, a SQL where clause without the where. It defines certain conditions around certain fields within a record, i.e., indicator can only be a Y or an N, or this value must be greater than 0. Now, Check constraints are very useful. They're very quick and easy to apply to files, and they can be, sorry, drink of water. They can be very powerful, very easy. You can have up to 3,000 characters per check constraint. So it can be a reasonably long where clause, which of course immediately begins to make it complicated. But you can have multiple check constraints as well. Same way as you can have multiple unique keys. So you can create quite a complex set of validations, because that's what check constraints are. They are validations on that particular file, but they are constrained to work within a single file. A check constraint cannot work beyond the boundaries of the file for which it is defined. As a result, you can't test that the value in this field is equal or is greater than the value in another file, in a field in another file. That you can't do. The fourth constraint is the big one. It's the referential constraint. The first three are all based on the file for which they are defined. But the referential constraint allows you to define a relationship between two physical files within a database. Now, we will go into each one of these in a lot more detail, and we will look at exactly how they work. But the referential constraints are the things that allow you to build your relational database, because they define the relationships, one-to-one, one-to-many relationships between physical files in the database. Now, there is a limit to the number of constraints that you can have on a single physical table. And I know that when I specified this last time, the last time I looked, it was 300. i.e., you can have 300 constraints on each physical file in the database. However, I think actually somebody looked it up and corrected me and said it was a lot more than that now. But quite honestly, 300 is an awful lot. So to have more is just an awful lot more. Okay, so the constraints made up of 4 different constraints form components of the database. Right. Then we have journals and receivers. Go into more detail a bit later, but journals and receivers are necessary for a fully defined DB2 relational database. So if you have not got into journals and receivers in your database, you need to start seriously thinking about it. We will talk about ways of implementing them, which are easy to manage and don't give you a great deal of hassle. But you cannot define referential constraints or check constraints without journals and receivers, because journals and receivers are used to manage the potential situation where you apply a record to the database and check its references, only to find that they're not valid and they have to reverse the update out again. So journals and receivers are used to manage referential and check constraint validation. And then commitment control. I insist, absolutely insist, categorically, absolutely insist that when you build a proper normalized database, you develop it in, around, and with commitment control. What we're trying to do here is we're trying to protect our database from all sorts of things, including accidental power failures that occur in the middle of a transaction. What you will find happening is as you start normalizing your database, you're going to get more and more files, and they're going to get smaller and smaller. Your applications will start processing transactions, and they will end up, a single transaction may update a dozen files in the database, with the knock-on effect that you will see from triggers. You could be updating a dozen files in the database. And if during that process you have a power failure or a system crash or a program error, you could end up with half-completed transactions in the database. And they are, if you face this at any time in the past, they are the absolute devil to clean up and get sorted out and make right. If you want to do it programmatically, you have to do or jump through hoops in order to make it right. Using commitment control takes all that problem and responsibility away. It protects the database from partial update as long as you utilize it correctly in your applications. But it needs to be an absolute non-negotiable part of the database. Those are the components that are actually, truly, and specifically part of the operating system to support DB2 relational database. There are two other things. Oh, sorry, I missed one. Why did I miss that one? I lied. There's the last one, which is absolutely and definitely a part of the physical database, and that is trigger programs. Or if one is going to be correct, triggered programs. These are programs written in any language you like, as long as it's RPG, in my case. You can hook them to any physical data file in the database. We will go into triggers in a great deal of depth because their power is beyond imagination. But they associate themselves, or you associate them, with a physical file. And those programs, through the database management system, create the intelligence that the database needs to become completely self-aware. And you write them in RPG, simple enough, easy to maintain, easy to test, and they attach themselves, or you attach them to a data table, a physical database file. And once they're attached, they are autonomous, and they do the job and protect the database without you having to worry about them. And they are definitely the thing that makes this whole thing work. So that list of components are operating system defined and operating system implemented. The trigger programs that you write in RPG that are attached to a physical database file run at priority 0 in the machine in the machine pool. If you are aware of any or understand work management on the IBM you have a machine pool, which is where all the operating system runs, at a priority 0, which means that it has preference over everything. And because a trigger program is part of the database management system, it runs there as well. So the performance from trigger programs is absolutely and utterly unbelievable. And you can do some experiments to prove it to yourself. Right. Having been caught once, I'm looking, and now I'm not going to get caught again. There is another element, which I call input-output servers. one of the things we want to achieve is we want to decouple, unlink, separate, tear apart, whatever you like to call it. We want to take the database away from the application, and we want to give it its own agility, its own management, its own intelligence, and we want to separate it from the actual processing that is done by the application. And the main tool to do this, the main tool that is used to do this is the input-output servers. Input-output servers are RPG programs, usually written as procedures and bound into a service program. And in my case, recommendation is one server for each physical file in your database. These are border control. They control the type of access that people have to database files. And in fact, I will show you techniques where, in fact, they protect your database from unauthorized access by a SQL client that somebody has downloaded from the internet. The input-output servers, together with the trigger programs, together can make your database completely impenetrable to anything except authorized programs, and it can be done without requiring any effort or management by anybody on your part. It becomes a natural consequence of how you put these together, and of course, details of those to follow. So, input-output servers, although they may appear, they're not officially a part of the database components per se. I see them as part of the database components. In fact, every time I create a database file, I define its constraints, set up its journaling commitment control, I define and code trigger programs for it, and I code and compile an input-output server for it. It's just a normal, ordinary part of the way we do things. Then the last component that I see as part of the database are things called enterprise servers. Enterprise servers are a sort of half and half. And I think if you remember, I showed you I'm going to find it and bring it up quickly. So that I can just refresh your mind. It's 21. What is this one? Sorry, I'll find it. Right, this was the slide. There's your physical database, DDS to DDL if required. The logical database we haven't discussed yet, but we will. There are your trigger programs, which are a component of the physical database. There are your I/O servers, and there are the enterprise services. Some of them sit more on the database side of the model, and other enterprise services sit more on the application side or the controller side of the picture. But generally speaking, the enterprise services specifically, there are certain types. Things like value-added tax or taxation calculators, discount calculators, quantity discount calc. There are many of those that really have application across your production systems. So they can't really be considered part of any production system. But they also they don't relate to one specific physical database file. They relate to a number of database files, and they produce a result which may come from multiple files. As a result, those ones tend to be in the model or the database side of the enterprise. Others are much more application code. When you create an enterprise service where the application code wants to display details of a customer, it simply pumps a customer number into an enterprise service and gets a response which returns all the information that it needs about that customer from 16 different physical files. That is much more an application service rather than a database service. So that's why the arrow runs into the middle. But I do include them as part of the database. Now I've got to try and get back to where I was, which might be a little bit tricky. Here we go. Okay, let's see whether we can. There we are. Hey, I found it. And it's even got the... So those are the components that we're going to be talking about in some detail. Remember, the biggest effort in modernization is around the database and its components. You want to make the database more agile, more self-dependent, self-reliant. You want it to protect itself against clients that shouldn't be there, and so on and so forth. And so we'll be talking a lot about these DB2 components. Right, physical database. I'm not going to go into this in much more detail. There are two types of physical database file, the DDS physical files and DDL tables. And as we've already discussed, it's not actually that easy to tell the difference between them. And there are very few things that behave differently between them. I will highlight what happens that is different between a DDL table and a physical file when we get there. Let's have a look at the construction. All physical files, no matter what type, the object firstly consists of a definition. The type code is star file. Its attribute is PF data. Either of the two files, they still PF data. And the first component in the definition is the definition. It's a section of the object that makes up the physical file. The next section is the data member itself. Of course, this is dynamic, and it's not part of this course to go and discuss how the IBMI spreads its data all over the disks to balance head movement and everything else, but that is also the most amazing algorithm. But the data member is what contains physical data records. There are two sections to the data member. One is fixed length fields, the other is variable length fields. And we'll come to that a little later, but they are in separate parts of the data member. We have an access path. Up until this point in your life, it used to be optional. Please understand the access path is in fact the unique primary key of the file and is no longer optional. It should be there for all physical data files. Obviously, there are exceptions to the rule, and there may be some physical files that it is just not worth having an access path for, because you're not including them as part of your relational database. Don't think that what I am saying cannot be reviewed and adjusted according to the need, because it can be. There's no absolutes in this game, none whatsoever. The last component of a physical file description are its authorities. And these authorities are actually, are a unique component of the IBMI and its predecessors, in that the actual object itself determines who can and who can't have access to it. Most other access or control or authority systems are based the other way around. You specify the name of the user and what objects that user can do and what rights that user has to each object. Whereas in IBMI's case, the authorities determine who can and what they can do with each individual object. So authority definitions are part of the database and not part of the application. So that makes up the physical database file. Let's have a look at the definition. Inside the file definition, and I must stress this, inside the file definition, it's got nothing to do with the application. It's got nothing to do with your business logic. It's got nothing to do with it. Inside this definition are the constraint definitions. The primary key definition, the unique key, the check constraint, and the referential constraint are defined within the physical file. Also, you can have a maximum of 300 of those. I tell you, even complex databases, I haven't got past about 8. So 300 is more than enough for most things. Although probably some of you have got systems where you might push the limit. I hope not, because they're going to be difficult. Inside the file definition are the definitions of how the file is being journaled. It's not external, it's inside the file. So each file knows how it's going to be journaled, where it's going to be journaled, and what is going to be journaled. And then also inside the file definition are 7 triggered events: before insert, before delete, before update, after insert, after delete, after update, and after read. You can have up to 300 trigger programs attached to those 7 events. Which means, but very obviously, you can have multiple trigger programs attached to a single event. Again, a little later, we will get into it in much more detail. But these are the important things that are held within the physical file definition. So all the components, with the exception of the I/O servers and the enterprise servers, are all contained within the file definition. Each file contains these definitions. And you can see them all. If you do DSP, FD, you can see the whole lot. If they don't appear, they're not defined. That's as simple as that. Okay. Sorry, I'm just talk too much. Let me rather than do this, let me just take a little pause and ask if there are any questions at this point in time. I know this is a lot to take in. It may be very familiar to some of you. To some of you, it may not be. And in fact, in some cases, people have said to me, Yeah, there are plenty of questions, but I don't know what they are yet. And that's why I say, please, if something occurs to you later on, send it to me in an email. I'll do with anything else what I did this time is to actually put them up onto the presentation so we can go through them before we move on to the next lot. Okay, no questions at this point that I can see. Please remember, if you're going to send questions, send them to everyone so that I don't have to reread them. Good. Let's talk about RDBMS, the Relational Database Management System. This is a very large chunk of code embedded into the operating system. And if any of you had a mistaken idea that our client process could directly access a data table, let me remove that misconception straight away. There is no way any client can access a physical table on the IBMI directly. You have to go through the RDBMS, the Relational Database Management System. And RDBMS does an awful lot. One of the things that RDBMS does is it maintains on behalf of the job that you are busy running. It maintains a thing called the PAG object. The PAG object, Process Access Group, is an object that is created when you start a job. And it contains, amongst other things, the attributes for the job. It contains the FDT or file definition table for every single file that is open in the job. It contains the buffers times N, one buffer for each file that's open in the job. It contains the file record pointer times N, one for each file open in the job. It contains job variable values and also all other job-specific information. So every time you open a file in a client process, you add to the PAG object. The PAG object grows and shrinks according to the demands of the job. The important thing to remember about a PAG object is that the whole PAG, the whole object, has to be in memory for the job to execute. If there is no space in memory for a PAG when a job requires to execute, then other PAGs will be swapped out of memory. The required one will be swapped into memory, and then the job will execute until it gets interrupted, and the process will then carry on. People think that, sorry, if we have documentation on the file, we can use it. Yes, you can. AI does it better though, Ed. But I get your point. I was saying the PAG needs memory space for the job to execute. When a job interrupts, another job gets an opportunity to run, and PAGs get swapped in and out accordingly. It is a common fallacy that the IBM I or any computer can do more than one thing at once. This is not true. A computer can do only one job at a time. It appears to be doing multiple jobs at the same time, simply because it's swapping from one job to another so fast you can barely see it happen. if you have a memory constrained system, swapping PAGs in and out becomes a mission. And eventually, it gets to a point, if you have too many jobs in the system, that the operating system spends most of its time swapping PAGs in and out and has no time to actually execute any jobs. At that point, we have reached a situation which we call thrashing, where the machine is actually furiously busy, and you will see it at over 100%. It's furiously busy. The CPU is doing absolutely extraordinary amounts of work and not getting anything done. And that is always, or pretty much always, caused by a memory-constrained system with too many jobs running in it. So the PAG is a very specific element that contains job information, and specifically about the files. The best thing we can do to improve performance in our systems is to keep the PAGs as small as possible. And due to the fact that the tables are the biggest contributor to PAG usage, the fewer open data paths that we have running for a job, the smaller the PAG will be, and the better everything will perform. Okay. Moving on. Primary keys. One or more fields make up the primary key. The defined order provides the index sequence. And only the primary is available for RPG keyed access. There's one thing that one has to realize when you're working with a mixture of DDS and DDL files. In the old days, we used to create keys on our DDS files by using K entries at the bottom of the record definition. And if you compile that file with K entries at the bottom, it's not a primary key. It is a unique key, but it's not a primary key. However, if you create your DDS file without K-specs, you can still add a primary key, and then it's available for all types of keyed operations on the system. That gets a little confusing sometimes, and it's particularly confusing if you define a primary key which is different to the one defined by the K-specs. Then things get a little wobbly, because what actually happens is you end up with one of them as a primary and the other one is a unique key, which can cause some confusion, and I'm sure you can appreciate that. So let's have a quick look at what a primary key is defined like. Now, it is a constraint. A primary key is a constraint, and you can add it in one of two ways. You can add it, add PFCST F4, file A, in a library, and you can add it as a PRI key. Right. This here has got a plus for more values, and you can specify the fields that you want to define as your primary key. Maximum, I think, of 2,000 bytes. One field, two fields, three fields, as many as you like. And the records will be sequenced by the access path, top down, initial key, and then the second and the third and the fourth, major to minor keys. in that order, and when you read the file in a keyed sequence, that is the order you are going to read the records in. You give the constraint a name. Now, it might seem strange, I've just said to you that this constraint is part of the file definition. But the system also sees it as a separate object. And that is why it's got a name. It's so you can identify a specific constraint. Now, the default is *gen. If you are working through add0, add0 will give you a default name, which is not generated. If you have *gen, it's generated by the system. You have no control. There is some logic in how it's constructed. It's very long, and it's not very user-friendly. So AO's implementation of suggested name standards would be the file name for a primary key, and the primary key will have an underbar P at the end of it. The reason for that, of course, is you can only have one primary key, and therefore you don't need anything else. That is, let's just put in here, field 6, whatever it is, as the primary key, and field 1. That's the order, 6 and 1. And that adds the PF constraint, the primary the physical file or primary key to the physical file. That is a CL command, and it works exactly the same way on both the DDS and the DDL files. No difference at all. And this is the command that AO uses to apply keys. However, there is another OBJ. You can also include it as part of the SQL statement. It's not actually here because we don't do this. We add it afterwards. But you can include it as part of the definition or the statement that creates the physical table. But if you're using AO to build your tables, AO doesn't do that. It adds the primary key afterwards. So you won't see that here, unless I've got one that we did in an old way. Yeah, there it is. This was one that was created some time ago. And there's the statement that adds the product code as a primary key constraint to this file with that name. So it can be built in to the SQL that creates the table. Using AO, I think actually I must get rid of that, and I must I've done it again. It's when you've got this PowerPoint. I actually should have this thing on the other screen, but right, let me just escape this quickly. Sorry, I'm and then I will pull that off and start this again. The reason that we tend not to build the primary key at the same time as we build the physical file itself is because the physical file, sorry, the primary key creates the access path. And depending on how many records there are in a file, the access path can actually take quite a long time to build. So we tend to create the physical file first, and then, yeah, there we are. This is the newer version of the product, which is due to be released quite shortly. And it actually does give you the constraint as part of the create statement. When you need to see what the source is that is used to put it together. So I just wanted to check that to make sure that that was correct. It is. But when we build the table, we only add the primary key afterwards, and we use that add PFCST to add it. I tend in most cases to use the CL commands. There are, and I warned you, there are some differences between DDS and DDL. We'll come to that just now. Right, moving on. Unique constraints. Sorry, that pause was to turn the fan on because I'm getting very hot in here. Whereas I know some of you are pretty cold. What's a great idea, Matt? Oh, the documentation from the DSPFD, is that what you were referring to? One or more fields making up a unique key makes up a unique constraint. This unique constraint cannot be used within RPG. Cannot be used by RPG to process the file in a sequence other than the primary key. Remember, I'm talking about physical files here. I'm not talking about logical views, indexes, joins, or any of the other stuff that makes up the logical database. I'm talking about physical files. So although you can generate unique constraints, they only work from within the RDBMS. They're not available for direct client usage. They help you sequence or make sure that records don't duplicate on certain fields. They allow you to use them for relational constraints. I will be showing you quite a bit of that just now, and so on and so forth. But they are RDBMS internal constructs. It cannot be used by RPG. Right, now we come to probably the most complex concept And this is where we start talking very seriously about relational databases. Relational databases are made up of two files related together using a referential constraint. Now, a referential constraint joins a parent file to what IBM calls a foreign key file. I have to use that word because that's the one they use in all their documentation. The important thing to remember here is that the constraint is defined in the foreign key file. It's not defined in the parent. So all referential constraints are defined in the foreign key file and point upwards to the parent. The parent file, because of that, requires either a primary or a unique key in order to define that relationship. The foreign key file requires fields matching the parent primary or unique key exactly. Now, this is got to be carefully thought about. In my foreign key file, i.e. my dependent file, my child file, I have to have fields that match my unique key in my parent, either primary or unique. They have to match. They do not have to form part of the foreign key file's key, i.e. they do not have to form part of the primary key on this file. They can be anywhere. They can be attributes that are not part of the foreign key file's key. But they must match the parent's primary or unique key exactly in two ways: attribute and sequence. The actual data name of the fields is irrelevant. So when you define the constraint in the foreign key file, you're pointing it at the parent file, and the fields you choose out of your foreign key must match exactly the primary or unique key. Now, I will attempt, if I can. I'm checking it first on the other screen so that I can find one. Ah, there we are. Yep. I can show you one defined as it appears, as it presents itself inside AO. We have a master file. Don't worry about the color. This is my test environment, and I busted something, which I'm sure you're all infinitely familiar with. Should be green, but it isn't. But the information here is valid. I have a customer master file in my little database, which we will see a lot more of later on. And obviously, its primary key is customer. In fact, I'll show it to you. That's the record in the customer master file. It has a primary key of customer number, but it has also got the rep code. The rep code is not part of the key. It's a field, but that rep code defines the rep that owns that customer. Logical type of third normal form file. No problem. The constraint is defined here, and it is, that's its name, R0. is a referential constraint number 0. I've never ever had to go beyond 9, but if you want to, you can go A to Z. It's a referential constraint, customer master file. It's defined in and on the customer master file. Its foreign key is rep code. Its parent key and its parent file are the sales rep master file and the rep code on the sales rep master file. So what we're looking at here is a referential constraint defined on the customer master file and related to the rep master file in a relationship. We can have a look at that. I will I'm actually going off the reservation here. FD, looking at the constraint, there is the primary key constraint. Right, here we are. I found it. Oh, I was lucky. I'm so happy. Right, here is the constraint. This is a customer master file. And its primary key constraint has got that name, its type of primary, it's got a key customer number, one number of fields in the key, key length is 4. That's the primary key definition. Here is the referential constraint. It's a constraint name, cusmaster R0, and you can see it's within the definition of the customer master file. Take note of that. It's the foreign key file in this case. It's of type referential constraint. Check pending. I will go into some detail just now. The status is established and enabled, and then it refers to which parent. The parent is the rep master file. The parent key field is rep code. The foreign key field is rep code, and there immediately you can see the benefit of having consistent naming conventions for the same data element, because they match up and they're easy to understand. So I'll bring this back just now. What we have created here is we've created a relationship between this file and that file. And because the parent, which is the rep master file, has got rep code as a unique relationship, it's a unique key, the relationship here is a 1-to-1. It's a 1-to-1 relationship in this particular case. Because you are defining it from the bottom up, and because the customer number has a single rep code, it can only point to one rep code in the master file. Therefore, it's a 1-to-1 relationship. Let's have a look at some of the other information around the constraint. I'm just checking to see. There are a couple of other things that constraints, once established, that constraints can do for you. There are two rules that are driven by constraints or managed by constraints. One is the delete rule. And I'm going to go back. In fact, let me go back and actually bring up the add PF. So the same command, add PF CST. This time I'm going to use a and it's a ref CST. The constraint key is rep code. That is the field that is being used inside this foreign key file as the constraint key. The name I'm generating is CUSMST0 because that tells me that it's R0 for that file because it's defined on that file. The parent file is webmaster file. And I can get away with not filling this in because the default says take the primary key from the parent file or take any of the keys that match from the parent file. So I don't have to fill it in. These delete rules, the delete rule is very intriguing. And I will tell you right now that you as developers, when you understand what this is, will be very interested. It has a number of different values. No action and restrict. Now, I'm going to let you read those one day all by yourself, but they look almost identical. But they're not. So I choose either no action, which means that the delete rule is effectively not in effect. The other one that I use is a rule called cascade. And this rule says to the database management system that deleting a record in a parent file causes matching records in the dependent file to be deleted at the same time when data for a null parent key matches data for a foreign key. So when you delete from the parent, you will delete all records from the foreign key files that match the parent record that you are deleting. It's very, very useful for things like invoice header, invoice details. Means if you want to get rid of an invoice out of your database, you delete the header and the details are gone as well. It's not such a good idea when you have this particular constraint we're looking at now, which is between the rep code and the customer. Particularly if the customer is also cascaded into the invoices and the invoices are cascaded into something else. That means you can wipe your database out with a single delete. Not a good idea. So you have to use it with caution, but it does have an incredible amount of power in keeping orphan records out of the database in a lot of circumstances. So it's well worthwhile examining this every time you create a referential constraint between two files. Carefully examine whether the cascade delete is applicable or not. Remembering that I can have 20 foreign key files all linked to the same parent. I'm going to say that again. I can have 20 foreign key files linked to the same parent. If some of those 20 have cascade and others don't, when you delete the parent record, you're going to smash up your database because you're going to delete those that have cascades and you are going to not delete those that don't have cascades. So relationships built using the referential constraint are not tinker toys, and they must be considered very carefully. We draw relationship diagrams with great abandon in a lot of cases. They can be very powerful, very useful. They can cut down heaps of lines of code. They can manage the database very nicely. They can make sure that you cannot put a record into a foreign key file if there isn't a record in the parent file. I can make sure you can't delete a parent record if there are foreign key records there as well. These are all parts and parcel of the validation of the database that you can remove from your code because you don't need it anymore because the database is managing these types of relationships. But like everything else, a quick definition can give you an immense amount of power. But it can also, if you don't think about it properly, it can create chaos, which is why test environments must mirror production environments in every respect so that you can be sure that you are testing properly. I don't use set nulls. It's to do with null parent keys. I don't use nulls a lot in RPG database or in DB2 databases. Set defaults. Updates matching records in the dependent file when the data of one non-null parent key matches for foreign key. Okay. So I very seldom, if ever, I don't think I've ever used set null or set default. I use cascade where it's appropriate, and I use no action where it's appropriate. So that is your referential constraint. It has a huge amount of power, and this alone, I can guarantee, will get rid of 30% of the lines of RPG code that currently exist in your applications. Because this replaces every single set lower limit or chain to check for the existence of a record. It gets rid of complex routines to delete dependent records. It makes sure that you can't put in an orphan record. You can't put in an invoice line that doesn't have an invoice header. All of that type of stuff that we check, or we should be checking, and I say that with a smile on my face, that we should be checking within our application code can all be done away with. Because the database is doing it. And when you take it a step further, these relationships are handled by the database. Even the good old standby DFU cannot bypass these referential constraints. If I attempt to add a record into this foreign key file by DFU, and it doesn't have a parent file record, DFU will fail. Any SQL client that you choose cannot get past this because this relationship is built into the database. I've shown you bits and pieces of a little database we use to just illustrate all of these things, and I'll keep coming back to that as we go through. That's a referential constraint. I'm going to stop here. I'm going to ask, are there any questions? Because this is heavy, and if there are any questions about relationships, now is probably the best time to ask them as any. Yep. Perfect, Ed, except because we can only have one primary key, I just put P, I don't put P0. Check constraints C0 through C9. Referential is R0, and there's one other unique, is U0 through U9, because the unique constraint is also there. Okay, I'm going on to the next slide, which basically introduces you to my little mini database. It is a agnostic database. It has files. You will see that they have got some fields in them. We can try and play with data and so on and so forth to show you what happens. But these are the files that make up this little non-specific database. Where are we? Okay, Ed, that question about how to do the validation we're coming to, that will be done in the triggers. And the method of notifying the user will be dealt with there in great detail, because that is where the real power of this database is. And incidentally, people, the referential constraints will take about 30% of your lines of code out of your production system. If you add the trigger programs, you'll probably take another 30% of the lines of code out of your production systems by moving all the validations into the database instead of doing it over and over and over and over again in your applications. Yeah. Naming conventions we can discuss as we go along. We do discuss it later on in the course, but that generally are the constraint conventions. I use them. I find them very informative. And when you have a constraint error in your system, it pops up the constraint name, so you can actually go and look up where it came from. And you can use that name to filter in AO to look up the constraint in AO, because AO is the source of all the information about constraints, triggers, and all that sort of thing as well. Okay, let's just have a quick look at this little database. We've got a customer master file, and we've got a customer balances file. We have a rep master file, we've got an invoice header and invoice detail, and of course invoice details are related to the product master for the product code. So it's fairly straightforward where the relationships are. Rep number is this one. Okay, Demi asks if there are multiple referential constraints on the table and the insert fails due to a referential constraint, what's the best way to recognize which column caused the issue? In that particular instant, when you're talking about referential constraints, it's not any particular column. If, for example, let me just change my pointer option. If, for example, this constraint fails here, you will get this constraint name, which will be INV HDR F_R0 probably. And that will tell you that that constraint has failed. Now, looking up that constraint, you will see that the only relationship between these two is the customer number. So a constraint that fails can mean one of two things depending on what you're doing. If that constraint fails during an attempt to delete a customer from your file, it will mean that there are invoice header records associated with that customer, and the constraint does not have a cascade delete. However, if you are trying to insert a record into this file, and that constraint fails, it will mean that you are trying to insert a header record for a customer that doesn't exist on this file. So by understanding you've got a one-to-many relationship here, because one customer can have many invoices, the key on this file is customer number and invoice number. But of course, only customer number is used in this constraint. So depending on what you're doing to what file and which constraint fails, then you can determine where the problem actually is. And 99% of the time, it's either you're trying to insert a record that doesn't have a parent, or you're trying to delete a parent that has dependencies. That's pretty much most of the time what they all are. And you can have a complete network. This is a very simple one, and I'm sure you can appreciate that. You can have a network of referential constraints. I want to just use this diagram to highlight something that I couldn't discuss about normalization. Sorry, let me just erase all the ink. I just want to highlight something that I couldn't discuss earlier. Those two files. This is the customer master file, and this is the customer balances file. And what I'm going to do is I'm going to pull AO in, and I'm going to go into the workbench, and I'm going to show you what is in the customer master file. We have customer number. There is the field that I've always called record status. I always put it into every single file I ever build. It's 2 characters. Sometimes I use it, sometimes I don't. But it's so useful. If later on you want to do something with the status of the record, it's very useful to have it. We've got customer name, we've got start date, which was the date that the customer joined the company. We've got 3 lines of address, which of course are in violation. No, they're not. They came from the same dictionary element, but they've been named three different ways. We've got a postcode and we've got a rep code. So that is the customer master file. Now, the balances file has got the customer number. It has the record status. This one is extremely simple, but it has the current due and 30 days due fields. And obviously it would have 60 and 90 and a couple of other financial type of fields relating to the customer. Now, the question is, why are these two files different? Why are they separated? Because they are both based on customer number. Therefore, there's a one-to-one relationship between them. The master file and the balance file. There's only one master file, one balance file to each master file. Why have I separated them into 2 physical tables? And the answer to that is something that is built into the SQL engine in the IBM I. And these 2 files are separated because one is a non-volatile file. That is the customer master file. It contains information that doesn't change very often. And it's a pretty static file. And the customer balances file is a volatile file. It's dynamic. Every time a transaction goes through for that customer, the balances file will change. So there's a lot more activity on the customer balance file than there is on the customer master file. So when you're looking at DDL and you are normalizing for DDL files, you need to look at that volatility of the file and try and separate the static from the volatile, because the SQL engine performs much better because it can optimize the one. When you create the file, you actually specify it as a volatile file, and that means SQL can optimize it to perform better. It also helps because in RPG, as you know, if you update a file, you tend to update all the fields in the file. And that means you are updating the static fields over and over and over and over and over again, which is unnecessary. It's a performance killer. So that is one aspect of normalization, which I can now demonstrate, which I couldn't show you before. Okay. Trying to get my pointer. So this is the little database which we will be working around for the rest of this session. But let me get to the end of the review of the components. The last constraint is the check constraint. An SQL where clause without the where defining conditions to be checked as true. What happens here is you create a clause. You say indicate a field in YNM for maybe. Now, when you attach that check constraint to a file, it will not accept any record that violates that check, i.e. that check must be true. Otherwise, it will not allow the record to get into the file, and it will reject it with a constraint violation. And again, by looking at the constraint name, you can see which constraint failed. And this, Demi, is coming back to your question in a slightly different way. If you have check constraints on a file where you're checking a lot of different fields via check constraint, you have a little bit of an issue, a difficulty here, because in order to make it easy to find which field has failed, it would be better to have separate constraints for each of the fields you're testing, instead of testing them all in one big constraint. However, that inserts an overhead rather than checking it on a single SQL statement. So there's a little bit of a toss-up here. If you have one statement that's checking 5 fields, it could have failed in any one of the 5 fields. If you have 5 constraints, then the constraint number will tell you which field failed. So there's a balance. But I'm going to skim this one by saying that it is in all my database designs, I have hardly ever used a check constraint on a database file. And you must remember me saying that, because when we next week on Tuesday, you will realize and understand why I never use check constraints. Because triggers do a better job. And I don't want to do both. It's one or the other. Because check constraints are a form of validation. So are triggers. And I don't like having two solutions to the same problem. Okay. Journals and receivers, just a very, very quick rush through journals and receivers. You have a client here that accesses through RDBMS, accesses a table. Now, obviously, the journaling is defined within the table. How it's journaled, where it's journaled, and everything else is defined within the table and is available to the RDBMS. So what happens is that an image, both before and after image, if it's an update, will get placed into the journal and via the journal into the journal receiver when the update to the table has been completed. Now, very important to understand why we need journaling when we are using commitment control. I will have a record written into the table before I check referential constraints and before I commit the change and before certain triggers are checked, before certain triggers have been called. As a result, the journal entry is in the journal receiver before the insert, update, delete is actually finalized for the table. So if for some reason that insert, update, or delete needs to be rolled back, then the journal receiver is used. The client issues a rollback statement, and the journal receiver entry is then rolled back over the top of the database record. i.e., this extra leg here of rolling back the change only happens if something goes wrong and a rollback is requested, which is different from a lot of journaling systems where other journaling systems, they tend to update the record but don't apply it to the database. They store the updated record in a holding area. And only when that change is committed do they write it to the table, which means that there's this pending stage and then write to the table for every record, regardless of its validity. If it's a valid record, there's the delay to write it away to the table. What happens with IBMI is that the table gets updated, and only in the case where something goes wrong does a rollback occur, which of course we all hope to write applications that don't do that, in which case there's almost 100% success on the write, and that means that the loss of performance only occurs when there's an error and a need for a rollback. How you manage your commit rollback cycles is important, and that is part and parcel of how you write your application code. That we will come to later. Unfortunately, I keep saying we will come to later because we are going to come to a lot later. Okay, so if your application is satisfied that all its updates and everything else have been done successfully, then all that happens is that RDBMS increments the cycle number and unlocks the records, i.e., there's an absolute minimum of effort or performance degradation when there is a successful commit of changes to the database. And that's why the performance using commitment control and journaling is better than in other journaling types of systems. Okay, now, my timing has not been bad on this one. It isn't bad at all. Let's look at the next. Right, this takes us back to our okay. Sorry, this particular little leg was supposed to be disappeared and only appear when I click the button. This is just an indication of what to do or how you can expand your database without interfering with existing tables. In my customer master file, which I showed you, the master file has addresses. It has 3 address lines and a postcode. Now, that's not really very smart, and it's not really a good normalization technique, because it is quite possible that a customer might have more than one address. In fact, they might have lots of addresses. They might have branch addresses. They might have postal delivery addresses. They might have a lot of different addresses. So a better form of normalization would be to take those addresses out into an address file. I can then put in an extra field to indicate what type of address it is. And I can then link it through a referential constraint to the customer master file. So I then have a one master record to many address records. I can do the same thing for email addresses. I can do the same thing for telephone numbers. Contact details is the one I use quite often, which is a person's name, his email address, his telephone number, the switchboard number, so on and so forth. These are all information that in most cases you would find on the customer master file, but your flexibility is missing because you can only define one address. If you normalize, as I display here, then you can have many addresses to one customer master file. And this is the process of normalization. This is where you're going to find you get more and more and more files with fewer and fewer and fewer fields in them. They get many smaller files rather than fewer, very much bigger files. But they also give you a huge amount of flexibility. Agility is what we call it. And this is what we're moving towards all the time. Because here, if I have another address type, I can't think of one, but the customer may have a warehouse. And I didn't have customers with warehouses. Now I've got a new customer and I've got warehouse. I just add a type code, I got a warehouse address, and it fits into the system without a hiccup. So the more your data is normalized and the better it's normalized, the easier it is to adjust your system quickly to changes required by the company. Okay, there's more coming where this came from, but this is question time. We've got 4 minutes. And if there are any questions, or as I said before, if you think of them later, send them to be my email. Oh, well. Thank you very much for your attention. I want you all to have a good day. And we'll see you on Tuesday. Great stuff.